This is a lecture on the electric field due to a continuous distribution of charge, and we'll actually split it into two parts. So in this first part, we'll talk about the basic idea, which is that you need to construct an integral in order to solve a problem of this form. And most of the work will be in the process of constructing an integral, and that's what we're going to cover. But one of the last steps of this process is that in the construction of an integral, you'll create a sum, and you hope to put it into the form of what's called a Riemann sum, which you might remember from your calculus classes, because a Riemann sum is in fact, the limit of a Riemann sum is the definition of an integral. So we'll do a quick math review of what the Riemann sum is and how we're going to use it, how we recognize it. Then I'll give you an overview of charge densities very quickly, of the kind of charge densities that you might encounter and how they're used in problems like this. And then we'll do an example, which is that of an electric field of a rod of charge. So part of that will be the construction of the integral, constructing those sums, and then separately we'll solve the integral. So that last part is really just a calculus problem, but I'll go through it for you as well. In the next lecture, we'll deal with a couple more complicated examples. So a two-dimensional example of a disk, but we'll get there by doing a ring. And in that, we'll talk more specifically about the idea of symmetry and how that can help you to simplify the solution of a problem like this. So let's start by talking in general about what we mean by the electric field of charge distribution. So just a reminder, in the previous lecture we talked about how to find the electric field of a point source. So we know that the expression for the electric field of a point source, point charge Q, is given by this. That came basically directly out of Coulomb's law. Sometimes we might express K in a different way, which is 1 over 4 pi epsilon naught. So it's K and epsilon naught are both expressions that we'll use for the electric constant, and this is how you relate the two of them. I think I'll use K for this lecture. And what we found was that if you look at a point in space near a source charge Q, then the electric field will point away from a positive source charge, and its strength will drop off as 1 over r squared as you get further from that source charge. And then we also looked at what if I had multiple source charges, and we found that you just simply add up the electric field contributions due to each source charge to find the total electric field at some particular point in space. So if we now want to look at a charged object, the basic idea is that you chop up the object into pieces and you treat each piece as a point charge. So let's draw a little example. Oops, I guess I want to do black. We'll draw a little example of a rod, and we'll assume that this rod has a charge Q, and maybe it's uniformly distributed charge. And then we want to say, let's find the electric field at some point P, which is directly above the rod and maybe above its center. So we want to find the exact expression for the electric field at point P, but we can no longer just simply say we have point charges that give us that expression. But an intermediate step before trying to look at the entire rod is to say, well, I can approximate it as point charges, meaning I can just chop this rod up into some finite number of pieces, like that. I can call this Q1 here, and this Qn here, so I have n, capital N pieces, and maybe this particular one I could call Q sub little n, so it's just one of the pieces in the middle, and we can assume that those are small enough that they can be treated as point charges. So then the electric field at point P, as we found last time, will just be the sum of the electric fields of all of these capital N point charges. So we could draw the electric field of little n, of Q little n. It's going to point sort of directly away as long as Q is a positive value. So I could say that this is E sub little n here. And in fact, we could draw all of them. So we only have, what do we have, like 9 of them here. So you're going to get some vector that looks like this for the middle one. You're going to get some that looks like this and like this. for the side ones, and then maybe there's another one that reflects that one that we drew already, and then there's another 2 more, and then maybe 2 more. So just thinking sort of how this works, the electric field at this point will be the sum of all those little vectors due to the point charges. And of course the sum, you can see graphically, would lead to something that looks like maybe this electric field vector. So just by sort of playing with that idea, you can see sort of what the electric field looks like. The point of this lecture is to try and make all of that more precise and give you a method of how to do it. But that's the basic idea, and it sort of just generalizes what we already know. The next step in the idea in making it more precise is that you'll write down that sum. So maybe we can write it down as the expression that we already know, which is the electric field at some point is equal to the sum of the electric field from 1 to n of the contributions due to each point charge. And I'm going to say approximately equal to, because of course these are not point charges, they're just chunks of charge right now. So that is an expression for the electric field. And then the last step is that you take the limit as the number of chunks goes to infinity. And that is how we define an integral. And we're going to show how to do that explicitly in a few moments. And then finally, once you have an integral, you just do calculus, and that's not physics anymore. You don't have to think there, you just have to solve an integral. Whether that's looking it up or knowing some methods in your head, that's really just all math, and we'll go through that. A little word of caution here, though. Remember, you're asked to find an electric field, so that means that you're asked to find an electric field vector. So in general, you can't just use a single sum in order to do something like this, but instead you're going to have to break it up into components. So you'll have a separate sum for the x component and a separate sum for the y component, and those two things will become integrals on their own. So you'll have to do an integral for each of the components as you go along. So I'm not sure if we'll see that today, because we'll figure out a way to restrict ourselves to one integral, to one sum. But in general, you have to remember, I'm looking for a vector, which means I need to find each component of that vector. And in this case, what that means is I need to do an integral for each component. So let's step aside and talk a little bit about math for a moment, because this is the tool that we're going to need in order to solve this. So what I want to remind you of is something called the Riemann sum. And what it is it's a way of approximating the definite integral of a function. So I've drawn a function here. This is a function of x, and I've drawn some bounds from x initial to x final. And the integral, remember, is just the area under the curve of that function. So if we want to approximate that, then we might say, okay, I'm going to use this as one point. That would be like my first point. I'll use this as a last point here. So that means that xi is equal to x1 and xf is equal to xn. And I'm going to chop it up into chunks. So I don't know what the easiest way to do that is. Maybe I'll just sort of subdivide it a few times. And then we can sort of So if we're interested in finding the area under the curve, you can see that it becomes the sum of rectangles. And these rectangles have a height of f of x sub n, little n, where I'm calling this particular one x sub n, and they have a width of delta x here. So that means that we can approximate the integral as the sum from n is equal to 1 to capital N of the area of the rectangle. So the area of the nth rectangle, which is going to be the height, f of x sub n, multiplied by the width, which is delta x. This thing is called a Riemann sum. So what does it mean to be called a Riemann sum? I guess it means that it has a delta x there, or whatever coordinate you're using, and it has a function of x, but of course it depends only on the discrete values of x that you found as you chopped up that region. So this is the Riemann sum. Now what's the use of the Riemann sum? Well, you can imagine that instead of chopping it up into some 9 pieces like I did here, you could chop it up into more pieces. And of course, as those rectangles get skinnier and skinnier, you get closer and closer to the actual value of the area under the curve. And the way we represent that is that the exact expression for the area under the curve, or the exact expression for the integral, is just the limit of the Riemann sum when the number of chunks goes to infinity. So you can see here that I've written out the Riemann sum here as I understood it from this picture. But if I take the limit of that as capital N, the upper bound goes to infinity, meaning that the rectangles are skinnier and skinnier, then that by definition is what we call the integral. So the integral, this thing that you're very familiar with, is actually really just symbolic notation for this thing up here, which looks a little bit more complicated, but has a pretty nice, easy expression in terms of breaking things up into chunks. So what are we going to do today? We're going to do some analysis to try and bring ourselves to the point that we get an equation that looks like this, to get an equation that looks like a Riemann sum. And then we simply say, okay, now I'm going to take the limit, and that means I get an integral, and then we'll get an expression that looks, that is something that we can easily do with calculus. And that last step, you notice, what happens is you send the xn into x and the delta x into dx. So that's just the way of writing this symbolic expression. And then, of course, you have to also figure out what the bounds are. So we'll do that along the way. One last thing about this, this math, there are multi-dimensional generalizations of this. So if you're in 2 dimensions, you could have an integral which is an integral over a function of 2 variables, some surface over 2 variables, integrated over area chunks, and this is dx times dy. That is by definition just the limit as 2 different number of segments goes to infinity, where you chop up both the x and the y directions, and then same thing for the 3-dimensional case, where you now have 3 sums there. Okay, so that's all math, and if you're interested in more details of that math and in probably a better explanation of it than I can give you, James Stewart's calculus book is really a great resource for you. If you don't have it, you might go grab it. It has many, many editions, so I'm sure you can find a cheap one online. But they go through these definitions of the Riemann sum in the 1-dimensional case, but also in the multiple-dimensional case. And basically all the math that we'll be doing in this course, which you might not have seen yet in a math class, is in the Stewart calculus book. So before we go on to the example, we just need to make a few definitions of how we're going to deal with charge. In the previous lectures, we talked about point sources, so we just said that we have a Q of a certain value. But in this case, because we have continuous sources, we need to separate out that charge in a way that we can represent the amount of charge per unit length or per unit area or per unit volume in the object. So the first case is the linear charge volume, and that means just the charge per unit length, and it's represented usually by lambda. So these are just conventions, but we'll probably use those conventions a lot along the way. So for example, if you want to find out for this, say, xnth chunk, the chunk that's sitting at position xn, which has a charge q sub n, well, that charge q sub n is just going to be equal to lambda times delta x. Because if you multiply a lambda by length, you get back charge. So that's what we mean by linear charge density. The next one is for surface charge, and so for problems like that, you can imagine that we will be chopping up these 2-dimensional objects into 2-dimensional chunks. So we might have here a delta A, some area chunk there, and delta A will have a q sub ij, for example, meaning that you'll need two integers to identify which of these chunks you're talking about, instead of one in the one-dimensional case. And q sub j will be equal to the surface charge density, which we call sigma, multiplied by that amount of area that it has. So sigma is the charge per unit area, or it's also called the surface charge density. And finally, if you have an object which fills three-dimensional space, then we have a volume charge density which is called rho, and of course if you chop up this object, you chop it up into pieces, but you have to chop it up into three-dimensional pieces. That's really an ugly picture. Let's just look at one of my chunks. So I'm going to have some chunk sitting inside there, which will be delta v, and that delta v is going to be labeled by three integers, delta v I j k, because you have to say how far in x, how far in y, how far in z you go to get to this particular chunk. And q I j k is going to be equal to rho times delta v I j k. It's going to be the volume density at that point multiplied by delta v I j k. And I guess I should write this out a little bit more clearly. It's going to be rho at the position xi, yj, zk times delta v I j k. So rho can be a function of the position, and that's the whole point, is that the amount of charge per unit volume could be different here than it is here, and we take that into account by letting rho be a function. The same is of course true up here, where sigma could be a function of x and y, and it's also true here where lambda could be a function of x as you move along this one-dimensional object. So those are densities. So now let's move on to the example. We're asked to find the electric field at a point due to a charged rod, and that point is located, we're told, along the line of symmetry of that rod. So this is the symmetry axis, and it's past the end of the rod. So the distance from the center of the rod to the point is greater than half the length of the rod. So some point along that axis is what we're trying to figure out the electric field. So what we're going to do is we're going to chop up the rod into chunks. We're going to deal with those chunks as point sources. We're going to add them up. We're going to find a Riemann sum, and eventually we're going to get an integral out of it. But a first step, which I didn't mention yet, is that you might take sort of a qualitative look at the situation to try and understand what is going on. So let's just make a little sketch first of that chopping into chunks. So if we have a rod and we chop it into a few chunks, and we have a point up here, what does the electric field look like? Well, it's going to be the sum of the electric fields of all of those chunks, and if we assume them to be points, then we know what it looks like. They're just electric field vectors that point away. Let's assume this is the largest one because it's due to the closest one, so maybe this is Q1 and this is E1. And then for Q2 it's going to be a slightly smaller E2, and then E3 will be slightly smaller, and E4 and E5 will be slightly smaller. So those are the contributing electric fields to give us the total electric field at that point. And we can see, without any calculation, that the electric field must point directly upward, up the page here. So what that means is we don't need to calculate the horizontal component of E. So if we draw an x and a y axis, we don't need to find Ex, we only need to find Ey, and the magnitude of Ey, or the absolute value of Ey, will be the magnitude of the electric field vector, and we know that it points up. So a little bit of qualitative analysis. Maybe I should say this is our qualitative analysis analysis above here. And now we'll move into the quantitative analysis. So we've remember that warning that I gave, which is that if you're asked to find the electric field, you have to find each component. You might have to do each of those separately as a separate sum and a separate integral. But in this case, a little bit of qualitative analysis and argument up front, which of course if you're solving yourself you should write out explicitly, allows us to say that the horizontal component is 0. I guess I should say that explicitly. So let's say Ex is equal to 0, and since I've introduced an x, I really need to say what I mean by x, so I draw a little coordinate system. So now we find Ey. So let's try it out. Let's draw right on the picture that was given to us. So we'll chop it into chunks, maybe 4 chunks on either side of the midpoint. I said Q1 was the top one before, but I think I'm gonna choose an x-axis, a y-axis that goes like this, and an x-axis that goes like this. So I'm going to just label them from the bottom to the top. So this is going to be my Q1, Q2, and of course this is Y2, and then I'm going to label an arbitrary one as Y sub n and Q sub n. The point of doing the sum is that you can focus on just one little chunk, so I usually label that and color it in, and you deal with it inside of the summation symbol, and that takes care of every single chunk, because the same thing should be true for each of the chunks. Some of the distances might be different or something like that, but the basic ideal will be the same. So let's try and write it out. So we start with the simplest expression. We're looking for the electric field at point P, and we're looking for the y component. And so what we say is that that thing is equal to the sum, where n goes from 1 to capital N, of the contributions of the electric field of each point charge in the chunks that we've made. And because n is finite here, it's only 8 or something, this is an approximation, so I write it that way. So this is really just a simple statement of our original principle of superposition, that the total electric field is the sum of the electric fields of each component here. Total is the sum of the components. And we take the y part of that equation, and that's what we end up with here. The rest of it is just very small, simple steps of logic. So the y component of the electric field at point P, well, I can draw that. So this is going to be En. This is going to be the electric field due to my y-nth chunk here. And what is that going to be? Well, it's going to be positive because my y-axis points this direction. And it's going to be simply equal to the magnitude. So Eny is just equal to magnitude En. The y component of this vector here is equal to its magnitude. First small step of logic. Next step, because I'm treating this as a point charge, I know the magnitude of the electric field. I have an expression for it, and that is K, absolute value Qn, over Rn squared. That's my expression for the electric field of a point charge. Next step, I need to show what some of those things are. So let's look at the denominator first, Rn squared. So what is that? Well, it looks like, if I were to draw it, it would be this distance here, R sub n. So how can I express that? And what I want to do, remember we're headed towards a Riemann sum. And it looks like we're going to be integrating, we're going to be adding things up as we go along the y-axis. So the Riemann sum should be a function of the y-coordinate, yn. So I need to be able to express that distance, Rn, in terms of yn. And it looks like, if I look at this distance here, it looks like Rn is equal to d minus yn. You see Rn is smaller than d here. Now, will that work for every value of y? What if I have a negative y, like down here at y2? Then I'll have d minus a negative number, so that will be larger than d. So it should work. So I can write that out. I can write that Rn is equal to d minus y sub n. And that whole thing is squared there. So I've arranged for the distance, and I've written it in terms of the coordinate that I think I'm going to actually be constructing an integral for. Now I need to do something with the Qn, and that's where the charge density comes into play. So we have a uniform charge here, we were told up here. So the charge density is just lambda is equal to total charge divided by total length. But the charge Qn here is equal to lambda times delta x. So I have a delta x on any one of these chunks, delta x. Each of them has the same length. I multiply that length by lambda, and I get back the charge of that chunk. So I'm going to write Qn in absolute value as lambda, absolute value, because that could be positive or negative, multiplied by delta x. Oh geez, not delta x. This is delta y. So this was wrong up here. This is actually delta y that I'm talking about. Delta y along the y-axis. Okay, so I can rewrite this a little bit, but basically I'm done with the construction of the integral. And that's because I've arrived exactly where I wanted to. I've arrived at a function of y sub n multiplying delta y. This thing is a Riemann sum. Okay, so now that I know it's a Riemann sum, now I can actually write it in the form that I'm most familiar with. I can say, all this time I've been saying EY is approximately equal to the sum, but now I can say that EY is exactly equal to the limit as the number of chunks goes to infinity of the sum. So I'm going to write out the whole thing again, just to be precise. And this thing, let me give myself another page, is equal to, by definition, the integral. And remember, you take the function, you replace the yn with y, and you take the delta y and you replace that with dy. So I end up with k, absolute value lambda, over d minus y squared dy. And the last step is I need to set the bounds of this integral. So I need to know what I'm integrating over in y, and that's clear from my picture. You can see that we have the start of the rod down here at y is equal to minus L over 2, and the end up here at y is equal to L over 2. So the bounds on my integration will be minus L over 2 to L over 2. So that's really all of the physics. That's all of the new stuff that you're learning about how to construct an integral. And the rest of it is now just a math problem. So I'll move on and I'll do that integral, just so that you can see that it's possible. But you can, of course, figure out how to do that integral on your own. And I'm most worried about you understanding how to do the construction of an integral. The rest of it, this calculus part, is really just a math problem. It's not really part of this course. But let's do it anyway, because we need to figure out what that is. So EY we have equal to the integral from minus L over 2 to L over 2 of k lambda d minus y squared dy. And this integral is actually not that hard to do. Of course, I can say that because I've already seen it, but it's not that bad. So let's try and put it into a nice form. That's always the first step of doing an integral. And in order to do that, I want to remove the constants from there. So I'll make this k lambda out front. And then I'm going to take the d outside. So I'm going to pull a d out from the denominator. So now we have 1 over, and I'm going to pull the d out. And then you can just imagine what happens as you distribute through. So it's actually a d squared that I've pulled out. And then I would get a 1 minus y over d here in the denominator. And we're left with dy. So you can check to see that that works. The d goes inside, you lose the square, you get a d, and then you multiply by d in the second term, and everything comes back to what we had. Okay. Now the next step is to try and simplify it. So the thing we want to simplify is this, to make it its own variable. So we'll do a u substitution. And so we get k, absolute value of lambda, I guess I should do the u substitution off to the side. So let's assume that u is equal to y over d. So that implies that du is equal to dy over d. So that means that I can take this dy and one of these d's and replace it with du. So let's do that. So we have a du. By definition, y over d is equal to u, so this becomes 1 minus u squared. And then I also need to take care of the bounds. So the u is just going to be the value divided by d. So this is going to be minus L over 2d to plus L over 2d. And my u substitution is complete. And now I just do the integral. And it's actually pretty simple. It might not be completely obvious just looking at it, but the result is, I have the k, oh sorry, I left out a d here. So I had one d that went into my dy over d to become du, but I still have one other d, so this becomes k lambda over d in both places. And it turns out that the answer, the antiderivative of this thing, is just 1 minus u to the minus 1. And you can check that yourself. If you take the derivative of that thing, you'll get a minus 1 from this factor, and then it'll become a 2, minus 2. But then you still have to go through with a chain rule, and you get another minus 1, and you come back to positive, so it works out. So we have minus L over 2d here, plus L over 2d. Those are our bounds. And then we can just rewrite it. So we get k lambda over d times 1 over 1 minus L over 2d minus 1 over 1 plus L over 2d. And we could simplify that if we want to. So how do we do that? Well, we could do, we could multiply each by the denominator of the other. So then we get k lambda over d is 1 plus L over 2d minus 1 minus L over 2d all over, when you multiply those things together, the two denominators, you get 1 minus L squared over 4d squared. The cross terms drop out because of the plus and the minus. So we get k lambda over d multiplied by, we have 1 minus 1, and we have L over 2d minus L over 2d, so we just get L over d all over 1 minus L squared over 4d. squared. Now, where does that leave us? Well, we can pull the L over D out front, and L times lambda will simply give us back the charge of the rod, because we said that it was uniform. So we'll just get a K times the absolute value of Q by pulling that L out. And then the D will appear in the denominator, so we have a KQ over D squared. And then we're left with 1 over 1 minus L over 2D squared. So that's the expression. That's the expression for the electric field magnitude at a point located above the rod. We can write the whole thing out in one piece, which is that based on the coordinate system that we chose, with x and y like this, we have Ex equal to 0 and Ey equal to k, absolute value of q, over d squared, times 1 minus L over 2d squared to the minus 1. And that's our expression for the vector. We could take it one little step further and say, what if we, for example, get very far away from that rod? So if our rod is here, and we make our D very, very big, so we're way out here where D is much, much greater than L over 2. In that case, then the ratio of L over 2D is much, much smaller than 1. I just rearranged that equation there. And so this piece right here will go to basically 0. And this whole thing will become just 1. So in the case that you go very, very far away, I guess I can write that out. So this is D much, much greater than L over 2. You just get 0, comma, KQ over D squared, and it basically just looks like a point charge. So very far away from a rod, the rod sort of collapses in our view, and it looks like a point charge, and the electric field expression looks like a point charge. So that completes our video of the first part of electric field due to continuous charge.